Morning, everyone. This is the session of the SEIO Women Commission, organized by the SEIO Women Commission, and Eva Vallada is one of the coordinators of this commission. And okay, she's the chair of the session. I'm the president of the society, and I want to say only a happy International Day of Women in Science and Data Science. Okay.
Thank you very much, Begoña. So good afternoon and welcome to this fantastic session with three speakers. This is the session organized by the Women Commission of the SEIO, the Spanish Society of Statistics and Operational Research. And we have three talks, different and relevant women, researchers at different stages of their careers. So María Jaenada, Vanesa Guerrero, and Lola Ruiz, thank you very much for your participation. So our first speaker is María Jaenada. She is assistant professor in the Department of Statistics and Operational Research at Complutense University of Madrid. She holds a degree in mathematics, a degree in mathematics and statistics, and a master in computational statistics. She recently obtained her PhD in mathematical engineering, statistics and operational research, and her research interests are information theory, regression models, high-dimensional data, and robust statistics. So Maria, thank you very much for your presentation. So you can start when you want.
Thank you very much, Eva, for the presentation. Okay, I'm sharing my screen. Just let me know if you can see. Okay.
Okay, perfect.
Okay, so thank you. Before I start my presentation, I would like to thank Eva and Begoña for inviting me, and the two colleagues, Vanessa and Lola, for sharing this session with me. This is for me an honor to be here representing all women in the science and in particular in statistics. I'm talking today about a little bit about my research. My PhD was about robot estimation for interval censored reliability experiments. As Eva just mentioned, I have just obtained my PhD in the last year, so I am my first stage of my career. So my PhD dealt with reliability inference, and to explain a little bit more about that, I will introduce some key concepts on this reliability inference. So first of all, what we understand by reliability, we think or we understand a product is reliable is it has the ability to perform its intended function without failure or breakdown over a period of time. A reliability test is then a systematic and controlled experiment conducted to determine the reliability of the product. What we do is the part of the inference. So we statistically analyze the behavior of the underlying products by analyzing the observed failure time in reliability tests. In reliability experiments are often occurs the censoring in data. This censoring occurs when incomplete information is available about the survival time of some devices. That is, the exact failure times are not known, but we may know some certain upper or lower bound about this failure time or the functioning state. Because we can consider different types of censoring, a statistical model tailored are required. This form of censorship will significantly influence the choice of this statistical model. In particular, we are focusing on interval censorship. This interval censoring arises when the items cannot be inspected continuously, but only at some times, some pre-specified times points during the experiment. So our experimental setup will be as in this figure. During the experiment, the failures will occur anytime. Here denoted by the cross during the experimentation, but what we can see is just the functioning state of the devices at these times, at this point, purple point, T1, T2, T3, etc. So what we can observe is the number of failures occur between these two consecutive times of infection. So what we record, what we see is the number of failures occur between two consecutive infection times. Here denoted by N1, N2, N3, etc. So if one could know the lifetime underlying the failure behavior of the devices, a multinomial model with probabilities of failures obtained through the cumulative distribution function, the truth cumulative distribution function, could be fit to the observed data. And this is what we are going to do for inferential purpose. Some example of practical use where this interval censoring occurs. So it may arise in experiments when are intermittently monitored, maybe in experiment when a functioning test is needed for need a manual check, so we cannot continuously check the functioning state, and only when the manual checks is performed, the functioning test can be performed. Or one last example is in non-destructive conscious devices, which was the primarily motivating examples that's developed of our research. So the main idea is that all surviving units that have not failed until the inspection time can continue with the experiment, providing extra information for inference, which in highly reliable tests is very convenient, as we have a very few information. On the other hand, we will deal with highly reliable products. Most of nowadays products are highly reliable with large mean lifetime to failures. Let's think, for example, of airbags in automobiles or batteries of our phones or laptops. They will have very large mean lifetime to failures. So if we want to perform an experiment under normal use condition, it will require very long experimental times, and we won't observe many failures. So this experimental design under normal operating condition will require a compromise between accuracy, the minimum number of failures that we need to observe for accurate inference, experimental times, and consequently cost. Alternatively, we could identify an external stress factor that influences the reliability, the wear and tear of the product. And then by increasing this stress factor, by increasing this external stress factor, we can accelerate this wear and tear of the product, so to induce a higher number of observed failures by subjecting these products to higher than normal stress levels. So after accurate inference of these observed failure times under these higher than normal levels, we need to extrapolate the results to normal operating condition. So what in particular, we are considering the step stress accelerated life test that is a particular experimental design consisting on increasing the stress level to all devices under test at some specified time of stress change. So the experimental design will be as in the plot. We will hold a constant stress level between two consecutive times of stress change, and at this point, here denoted by tau 1, tau 2, until the end of the experiment, we will increase this stress level and hold it constant until the next time of change. Joining up together the challenge or the condition of interval censoring and the high reliability of the accelerated lifetime test, we will have the observation as in the plot. We will have the count of failures, as I have explained before, but this count of failures will be observed at different times, at different stress levels. Here, for example, the first two count of failures was observed under stress level X1, while the next one is observed until second stress level X2, and this process can be continued until the last time of stress, until the last stress level at the last count of failures. So we will need to manage these two things, count of failures and stress level at which it has been observed. As I just mentioned, we want to extrapolate the results to normal operating condition. So we will necessitate a model relating lifetime distribution of the device at the stress factor at which they are held. For this purpose, we usually adopt a log linear model relating a scale parameter or rate parameter of the assumed lifetime distribution to the stress level, here denoted by X. So in reality, our model parameters will be this A0, A1, defining the log linear relationship. This log linear relationship fits with some important physical models as, for example, the Arrhenius reaction rate model for temperature or inverse power law for voltage. And that's why that's commonly adopted in practice. So until now, I have just explained the statistical model and the multinomial model we use and the observed data, the count of failures observed. In a classical approach, we will use the maximum likelihood estimator to make inference and then analyze the result. These maximum likelihood estimators enjoys very good asymptotic properties, including efficiency, consistency, asymptotic normality, and many other good and desirable properties. However, it will lack robustness, meaning that it will get easily influenced by contamination in data. In this regard, we propose an alternative robust estimator that are resistant to those outliers. This robust statistic has gained a growing interest in many different statistical models in the recent decades. In particular, we adopt the minimum distance estimator class that is a class of parameter estimation methods in which the estimated parameters will minimize the distance between the theoretical model assumed and the empirical distribution, the empirical data observed. The key idea is to find parameter values that make the assumed model as similar or as close as possible to the observed data. And for such purpose, we can assume many different measures of closeness or similarity. It will depend on the measure you choose to consider two different probability vectors close. The resulting estimator will have different properties. For the robustness purpose, we have chosen the density power divergence, which has gained popularity as it has shown very efficient estimators and very robust estimators in comparison with the maximum likelihood estimator. In our discrete multinomial model, the density power divergence is as in the first formula given here. This is a quite ugly formula, but let's just focus on some details about it. So first of all, it's indexed by a tuning parameter beta, which will determine the compromise between efficiency and robustness on the estimation. Indeed, for beta equals 0, it will coincide with the maximum likelihood estimator. So it will be the most efficient but less robust of the family. Because this is a measure of closeness, what we want is to minimize the distance, the pseudo distance or similarity between the empirical probability vector obtained with observed data and the theoretical probability vector obtained from our assumed cumulative distribution function. Once we have all formulas written, we can obtain the asymptotic properties of the estimator. I won't stop a long time here, just mention that we can obtain the estimator as the solution of a system of equation with Makis M estimator, and this estimating equation will depend on some matrices which are defined in terms of this probability of failures and its derivatives here. Using these previously defined matrices, we can obtain the asymptotic convergence, the asymptotic distribution of the estimator, and in particular, we can see that it is asymptotically normal with this asymptotic variance-covariance matrix, which will allow us to define asymptotic confidence interval for our estimator too. So as we will have for the MID, for the likelihood estimator, we can also obtain point estimation and asymptotic confidence interval for our minimum density power divergence estimator. With this in mind, it just best to choose lifetime distribution for the model. We could assume any of the common distribution for lifetime data, like exponential, wave, gamma, log normal, and so on. Derive the explicit expression of the estimator, estimating equations, asymptotic properties, and so on, and see how, or if they are robust, how they behave in practice. So just to show you empirical plot of the behavior, if we consider different tuning parameters here from 0.2 to 1 and jointly with the MID, and we contaminate the model. I not explain how I contaminate, but I did contaminate the model in the direction of the first and second parameters. We use any of the parametric lifetime distribution. For simplicity here, I chose the exponential one. What we can see is that in the absence of contamination, all estimator behaves similar, but when we increase the contamination, the error, the root mean square error of the MID grows up very rapidly, while our robust estimator keeps behaving a little bit better, obtaining a low error under very heavy contamination setups. Okay, I'm not in time for explaining any other things. I just wanted to thank again the organizers for having me here and the audience for hearing. Thank you very much.
Okay, thank you, Maria, for your participation, for your talk. So we don't have time for questions. So maybe at the end of the session, I don't know. So we are going to start with our second speaker. She is Vanesa Guerrero. She is an associate professor in the Department of Statistics at Carlos III University of Madrid. She holds a degree in mathematics, a master in advanced mathematics, and a PhD also in mathematics. And her research interests are focused on the use of mathematical optimization tools for problems related to the analysis of complex data. So thank you very much, Vanesa. When you can start when you want.
Thank you very much, Eva, for the introduction. Let me share. Can you see my presentation?
Yes.
Okay, let me just do this. Okay. So as I was saying, thank you very much, Eva, for the presentation. Thank you to SEIO for organizing this this session in this day. I hope you all have a very happy International Day of Women in Statistics and Data Science. And well, it's a pleasure for me to talk a little bit about the research that I have been doing with a PhD student. So this is, let's say, the second stage after Maria's research, who has just presented her PhD research. So this is the first PhD thesis that I have been supervising. Well, the title of the talk is Enhancing Interpretability in Additive Models via Mathematical Optimization. And this is, well, the structure as usual, a short introduction, some preliminaries about the tools that we have used to study this problem of interpretability in additive models. And in particular, I will speak about constraint smoothing and feature and functional form selection, and finally some conclusions. Well, as I said, this is a PhD thesis that I have been co-supervising during the last 3 years and a half, more or less. And well, the title is, you have it here, Constraint Smooth Regression Models, a Mathematical Optimization Approach. And well, in particular, I will speak a little bit about 3 problems that we have studied in this thesis. Well, the PhD student is Manuel Navarro Garcia, and I co-supervised him with María Durban, who is also a professor here in the Department of Statistics at Carlos III University in Madrid. Well, in this first work that you can see here, what we study is, let's say, a univariate regression model in which we want to estimate this function f in such a way that it is smooth, but also that it verifies some shape constraints in the sense of sign or monotonicity or curvature constraints, as I will explain in a minute. In this second work, we generalized the previous approach to the case in which we have an additive model in the sense that we may have main effects, which are treated as univariate functions, and also interaction terms. So we had to study the problem of imposing these shape constraints also on multivariate functions. Here I wrote the model only for 2 covariates, but the work that we have developed holds for any number of covariates. And finally, the feature and functional form selection problem in additive models. So we think that with this general overview, in the end, we are working, of course, in the field of interpretability, in the sense that we are providing expert knowledge to the model, and also trying to simplify somehow the additive model in this case by selecting the appropriate number of variables and also in their appropriate functional form. Well, of course, as I have already said, it's crucial to have models or statistical models or systems that are able to incorporate human knowledge and also to provide, let's say, meaningful support to the decider. And indeed, with the noisy data that we typically have, is very important the idea of smoothing, no? Of being able to estimate these smooth functions that do not capture the noise, but the general trend in the data. As I said, we are going to study the problem of imposing some constraints in the domain in which the function has to be estimated in the sense of the domain in which the data have been observed, but also in order to carry out constrained out-of-range prediction. This is either forward or backward prediction, imposing these constraints. The research, one of the motivations for this research was this plot that we saw in Spanish media during the COVID-19 pandemic, in which we saw that the number of fatalities per day, the estimated number of fatalities per day, if you look at the region of Aragon, it was estimated to be a non-negative number, a negative number. And in fact, that was something that was not realistic in practice, and that's why smoothing techniques have to be aware of this kind of conditions, and not only sign, but also curvature or monotonicity, as I said. And of course, about feature selection, we all know how important it is to identify the appropriate number, not only the number, but identify which are the features which actually affect our model in order to reduce overfitting or increase predictive power. And what we found out is that most of the work about feature selection was done in linear regression and not that much in the context of additive models. And that's why we try to contribute to the literature in that sense. And in both cases, and something that I have not mentioned specifically yet, but I'm going to do it now, is that this research establishes a new bond between statistical modeling and mathematical optimization, because optimization is a mathematical optimization model is what is behind all these problems that we have addressed in Manuel thesis. Well, regarding the constraint smoothing and out-of-range prediction in this additive model that I showed you before, as I said, with only two covariates, but it works in general, we are going to use a basic representation of the functions using p-splines, and we are going to use a conic optimization approach in order to estimate these smooth functions, as I will show you in a minute. And regarding the feature and functional form selection problem, we are going to exploit a reparametrization of these smooth functions such that they can be decomposed into a linear and a non-linear part. And we will be able to decide whether a variable has to be in the additive model in a linear manner or in a non-linear manner or in both manners, or if it does not have to be there. And in order to do that, we will formulate the problem as a mixed integer quadratic optimization problem. Well, what is a p-spline and what is a conic optimization? Well, in the univariate case, a p-spline is a curve that is estimated in the following way. So we consider a set of basis functions, which are here in the top figure. The bell shapes that you can see here below are p-splines basis functions. And what we do is estimating the blue curve, let's say approximating the data, which are the blue squares, as a linear combination of these basis functions. Depending on the number and position of these basis functions, the curve will be more wiggly or less, let's say. So in order to mitigate the effect of the selection of the basis functions, a penalty is added in the estimation process, and you can see the curve below, which is much more smooth, okay, than in the previous case. So let's say that this is the p-spline idea graphically in the univariate case, and this can be generalized to further dimensions using multivariate basis functions. This will be the example of one b-spline basis function in the bivariate case. So the idea is, in the bivariate case, being able to obtain surfaces which are smooth and that are obtained as linear combinations of these bivariate spline functions, b-spline functions, and so on and so forth for further dimensions. What about conic optimization? Well, maybe many people is not so familiar with this, but the idea or the standard way of stating a conic optimization is like this. We minimize a linear function subject to linear constraints and subject to the decision variables x belongs to a cone. Okay, there are different types of cones, and the thing is that these type of problems are considered, well, they are as a class of convex nonlinear optimization problem, but there are efficient algorithms to solve them. So having a formulation like this is something that is in general manageable somehow. Well, so what we are going to do is formulating our shape constraint p-spline estimation problem as a conic optimization model, exploiting one result about non-negative polynomials, as I will show you in a minute. Well, in the end, in the univariate case, if we think about the kind of function that we are estimating, we end up having a piecewise polynomial of a certain degree, depending on the degree that we chose for the B-spline basis functions. Therefore, we can use this result, which is stated in this paper, but it's known. It was known before, which is, well, it has necessary and sufficient conditions to say when a polynomial of any degree in an interval is non-negative. So we say that a polynomial of degree s is non-negative if and only if there exists a positive semi-definite matrix such that its entries verifies this set of linear constraints. Okay, so the idea is that if we go back to the case of estimating a smooth curve such that it is non-negative, it is enough to impose these conditions to each of the pieces in the piecewise polynomial. And by doing that in that way, we are ensuring that the estimated curve is non-negative. Regarding the formulation, it looks like this. Of course, I'm not giving many technical details, but well, everything that you can see in color is a decision variable, and everything that is written in black is data. Some the optimization model regarding with the data, regarding with the linear constraints that I have just shown you in the previous theorem. And well, as you can see, linear objective function, these are a set of linear constraints, and then the second order rotated cone is involved here, and also the cone of positive semi-definite matrices, because recall that in the previous problem, some positive definite matrices appeared. So this is a conic optimization model, and solving this, what we are estimating is a curve that is non-negative. Using these conditions on the derivatives of the curve, we can add monotonicity constraints or curvature constraints, and so on and so forth. So this is, let's say, the basic formulation for the problem, but it can be enriched with many more properties. But this is the univariate case. What about the multivariate one? What happens if we want to estimate surfaces that verify some conditions either in one of the directions or in more than one or globally? Well, the thing is that there is not an equivalence condition that guarantees the non-negativity of the estimated surface or hypersurface when we are not in the univariate case. And what we have done, or the approach that we followed, is imposing these shape constraints that we have seen in the univariate case in some of the curves that belong to the hypersurface being estimated. So the idea is, what you can see in the plot is a surface in which you can see some red dashed lines. So in those curves, what we are doing are imposing the shape constraints that we have just developed for the univariate case. By doing this in this way, what we are doing is having a skeleton in the surface that ensures that in some of the bones, the conditions are met. Since the estimated surface has to be smooth, we hope that huge deviations do not happen and that the conditions are also satisfied in between the curves in which the conditions are imposed. Of course, these conditions are not equivalence conditions, but we have observed that it works very well in practice. Well, so with this idea, here you have some examples in the univariate case. The theoretical curve is in black, the unconstrained curve is in green, and here we have some confidence bands. As you can see, the green curve is not that close from the black one in some parts, and of course the confidence bands go below zero, even though the theoretical curve is not negative. With our approach, we are able to, of course, improve that curve that is being estimated. Also, we have used, we have developed an approach to carry out forward prediction or backward prediction. This is an example in which we have to impose that in the forward prediction, the curves do not cross over, because this is a biological application in which we assume that for older ages, the mortality rates have to be higher. So it is not possible that mortality rates became higher for people who are younger. And we are able to fix that with our approach and obtain better results than some state-of-the-art approaches. Also, in the bivariate case, we were able to fix some sign problems that we estimated in some examples, and also we applied our approach to the estimation of production functions successfully. Well, to give you some insights about the feature selection problem in additive models, so let's assume that each function in the additive model can be expressed in this way, as I explained before, as a linear combination of B-splines basis functions. Okay, in matrix form is something like this. So each function in the additive model is written as a product of a matrix of B-splines times a set of coefficients. So what we do is reparameterize this so that we isolate the linear part and the non-linear part. By doing this in this way, we have to estimate the beta coefficients that go with the linear part and the alpha coefficients that go with the non-linear part. And introducing binary decision variables that takes the value 1 if the jth covariate enters in the model in a linear manner or 0 otherwise, and the sj the same but for non-linear components. What we get is a mixed integer quadratic problem like this. So we minimize the estimation error subject to at least we select k components. So it is like the best subset selection problem. Here we have some constraints imposing the semi-continuity of the beta and alpha coefficients. So we have these big N parameters that we have to estimate and for which we have developed tight bounds and, well, the nature of the variables. Since this formulation works well in practice only for a number of variables in the size of the 40s or 50, we have also developed a math-heuristic approach, which is based, okay, I will do this very quickly, in the large neighborhood search idea. So if you want to know more details, I will be happy to give you more. So some results, well, I have lots of tables, but in 3 simulation scenarios, just a couple of comments. We compared our approach with other methodologies in the literature with a number of variables equal to 100 and 200, and our approach works very, very well in practice. In most of the cases, we are able to identify the correct functional form of each of the covariates and the variables that have to be there in each scenario. And I will show you also in terms of the predictive power, our approach outperforms the other ones in the literature. And let me conclude my talk with this plot in which I illustrate for one of the example, our approach is the blue one, f-sum, and the theoretical function is the black one. So if you take a look, you will see that the blue curves are always the ones that are closer to the black ones. So our approach is able to identify not only the correct variables that generated the response, but also in their correct functional form. Also, we tried this with real data, and just to conclude, saying that we have used mathematical optimization to address these problems in statistical modeling, and that we have two Python libraries, CP-splines and FSUM, for these two problems, the constraint P-splines approach and the feature selection problem that I have just introduced in this GitHub repository. And this is references. Thank you very much for your attention.
Okay, thank you very much, Vanessa, for your presentation. And we don't have time for questions, it's the same, but we have to continue with our last speaker is Lola Ruiz. Lola is a full professor in the Department of Statistics and Operational Research in the University of Granada. She holds a bachelor in mathematics and also a PhD in mathematics. She has a long academic career and research experience. So her research interests are random fields, functional time series, and manifolds, and she leads several research projects, a research group, and she coordinates the SEIO Women Commission. So thank you very much, Lola, for your participation. I think you are mute. You are.
Do you listen now?
Okay.
Yes. Sorry. Thank you very much for your presentation, Eva, and for also thank you very much to Begoña for the organization and to the above participants, which are excellent, both of them. And I am very happy to be here to present some feature of our research work. I'm only, I lost my screen, which is, I am sharing my screen. I am sharing, no? I am, Eva, I am sharing my screen?
No. Okay.
Okay. And now sharing my screen?
No.
But I am, for me, I am sharing, but I don't know. I try it again, please. This is.
I think now. Yes.
Now is yes?
Yes.
Okay.
Okay, perfect.
Sorry for the delay. Good morning then. I am going to present some recent advances in non-Euclidean functional time series analysis. Indeed, I will try to summarize some key topics in this framework, which are mainly related with manifold supported functional time series and manifold evaluated functional time series. Indeed, although the framework is quite theoretical, we are motivated by the real data example, like I try to reflect in this as few as likely, or as mainly reflecting key references and some interesting problem in climate science, in meteorology, oceanography, geophysics, astronomy and astrophysics, geophysics, medical imaging, computer vision and graphics, and also in economics, recently in economics and finance. What are indeed the kind of data we are going to analyze? We are going to analyze the curved data with value in a manifold in the second part, which is the manifold evaluated time series analysis, and also surface data, map data, especially of the Earth in the first part, which is called manifold supported time series. What are the main problems? The main problem are we have to work with high dimensionality, complex dependent structure, local and global analysis, low memory in non-Euclidean setting, and how we can address this problem in these two approaches. We can check the more recent references, for example, in manifold supported or functional time series. The suitable framework mainly are focused on sure dependence, like these first references, or with dependent process case, even in the spectral analysis, and also in long-run dependence case, we can find a few points and topics which is restricted only to 3 key references mainly. How it is the difficulty, because we add to the above mentioned problem the problem of long memory, which will be John Markovian setting, and then one simplification is lost, and then we have to reduce this kind of dimensionality via some restriction like stationarity in time and isotropic, which in our case is connected with, in the case of manifold given by connected and compatible point homogeneous space with invariance of the kernel we are working, which define the operator, the spectral operator family, are invariant against the group of isometric of the manifold. And these manifolds are very suitable because they have the good property are isometric to the sphere. And we are interested especially on address in a suitable way the problem of spectral analysis of long memory or LRD time series. In that case, we have to reduce the problem to a sequence of stationary real value time series and some with summability conditions on the family of second and fourth order spectral cumulant operator. We concentrate in one approach because until at least up to our knowledge, this approach had not been presented before. And then we have in the spectral analysis of LRD series as a parametric framework, we have 2 operator factors, one factor M, which is collecting the local features of our surfaces data, and other factor, which is omega to the power alpha, which is collecting by scale, manifold scale, the long memory, which is varying, scale varying. And in that sense, we have 2 operators, the LRD or long memory operator and the regular part. In the case we are considering that the purely parametric framework, then in the regular part we are some example, friendly example, motivated example, which is multi-fractional integrated functional time series. In that case, our regular part, them operator, have a spectra which is related to the so-called spherical Hilbertian autoregressive and moving average processes, which are has been now studied in recent literature about reflected in the previous slides. And in that case, this purely parametric framework, we can go for some special case of a point spectra of the RD operator, go to the Markovian case. That is the generality of the family of model we are considering in relation to the current literature. So for some example, in a simulation, we are working with with 2 main approaches. One approach is related to local high resolution analysis, which is based on legend transform. And in that case, we consider in the simulation, we are going to show for motivation with 30 scale. And in that sense, we have some spectral element. This is the a feature of projected in the 30 again space of the Laplace-Beltrami operator of the spectral density kernel of the family of spectral density operators at 4 frequencies. And also we have this factorization in the left-hand side. We have the projection of the kernel defining the regular operator, and in the right-hand side we have the 30 projections of the singular pattern defining or describing the behavior near to the 0 frequency of the governing by the LRD operator. What is about the estimation techniques we can apply here? We apply two techniques. One is based on minimum contrast estimation, which is very close to curva level divergence by the functional spectral domain. Then we are working with this kind of diagonalization of the kernel based on, again, function of the Laplace traveling operator using this kind of invariance of the kernel associated to our family spectral density operator. And then we can work with this kind of frequency varying eigenvalues of the spectral density operator and can extend in an easy way via the supremum norm of the operator, linear operator norm, the minimum contrast estimation. And then in the simulation, we consider, for example, one set of candidates here for the pure point spectra of the RRD operator and the true spectral point spectra of the RRD operator. In the left-hand side, we consider decreasing parting, the left and right-hand side, and increasing parting. And this is very easy example because here we have that our interest, which is in the dominance of a space where the projected process displays the largest dependent range, can be detected. It's not necessary to be estimated by this pattern, but usually this is one problem, is to estimate the dominance of a space where the projected process displays the largest dependent range. Here we have for this generated data set, we have the functional discrete Fourier transforms that are used in the computation of the periodogram kernel or the periodogram operator, which is the empirical statistic we use in the evaluation of this statistical distance in the functional case of minimum contrast estimation. And the result, the theoretical result we find in this kind of minimum contrast estimation is the weak consistency of the minimum contrast parameter estimate of the RRG operator in the Gaussian scenario. And beyond the Gaussian scenario, we have some nice result. Not only this, we have deeper simulation study with a lot of functional sample size, repetition, and so on. But we see that beyond the Gaussian case, the weak sense behavior with a consistency behavior holds. So we have to improve our theoretical result in that sense. And in our empirical analysis, we have also addressed another feature like the mean and variance of the empirical functional error or the asymptotic distribution by scales with different velocity and depending on different magnitudes of the error associated with our estimations. Always, these all results we are mentions are collected into contributions. One of them is part of the thesis recently supervised, which is co-author my PhD student Ovalle Muñoz. The application we considered of this kind of LRD isotropic functional time series manifold is the nonlinear functional regression in manifold, where H is the nonlinear operator which combines the geographical and temporal information with reflecting nonlinear association between the functional response and the functional regressor. In that sense, we also consider an extended version of the useful link, in this case, link operator H. Our simulations are now concentrated in a large scale analysis motivated by the real data application I show below. And in that case, we only consider spherical harmonics, 8 eigenfunctions of the Laplace-Beltrán operator. This eigenfunction, we consider the projected log error term, which is an RD isotropic functional time series as commented before at different times, because we are considering the case of sphere, and this is the clubbing prediction via this nonlinear regression model of this realization. And we consider also empirical analysis of the mean absolute error based on 500 repetition in this slide. The magnitude of the error are in the interval 0, as you say, at the magnitude 10 minus 3. But this is quite acceptable. And also we consider the plugin nonlinear regression predictor after estimating by minimum contrast and weighted period operator the second order structure of the LRD error term. And these are by scales, by manifold scales in the spectrum, and also this is the expression of the predictor. So in the simulations, the nonlinear spherical functional response generated is here in one realization in different times, and the nonlinear spherical functional response predictor with this nonlinear functional regression model, and the empirical mean absolute error based on the same number of repetitions. Also the same order of magnitude of this kind of mean empirical absolute error, spherical. So what is the real data application? In our case, we have considered the generation of synthetic data, and we have motivated by the prediction of downward solar radiation flux for predict this kind of solar radiation flux SMAP from atmospheric pressure, motivated by some previous references in that sense, where the authors made a pure spatial analysis. Here we introduced time, and we saw that this introduction of time is motivated. This is some detail of the synthetic data generation algorithm with the physical equation involving in the generation of the solar irradiance, and also the random perturbation as the definition of the log Gaussian error term in the model, the atmospheric pressure and the atmospheric pressure plus the unstructured part, and also some details about how one can obtain this kind of pattern, spherical pattern, usually observed, for example, in atmospheric pressure during autumn, winter, or during spring, summer. All the things are related to generate nonlinear spherical means from physical model and perturbated by LRD functional time series with some characteristic like isotropic assuming in our framework. Well, now what is the thing that we are motivating the second part or the talk? That is the manifold evaluated functional time series. This is the analysis of trajectory data, like in plane, or like, for example, in our real data example we are developing in the prediction of the orientation of Earth magnetic field from the observation of the spacecraft measurements. In that sense, we have two key references, which is Petersen and Muller, which provide some approximation by Fletcher regression for functional regressor given with value in a metric space, but functional response with value in a metric space, but with a regressor in Euclidean space. And in our case, we consider that both the response and the regressor is evaluated in Riemann, compact Riemann manifold. In that sense, we have to address in this framework the problem of minimization of Fletcher function, which is awaited in our case because we follow up Petersen and Muller. This kind of L2 center of map of the conditional measure to compute Fletcher mean is in our case considered by minimizing a weighted Fletcher mean involving like a integrated quadratic geodesics distance between the response and the curve in the manifold. In that sense, we need, for the global Fletcher regression predictor, some geometrical restriction, also to restrict some how the sample regularity, local regularity, and the dispersion of our curve data in the manifold. We have to assume or restrict the family of curve, bivariate curve manifold processes to the case of stationary energodicity, and we obtain with this all assumption the quick consistency of the global Fletcher regression curve predictor for manifold with some geometrical restriction. So in the simulation, we have three simulations to evaluate the performance of the three proposed Fletcher predictor: global, local, in Nadaraja-Watson time framework, and local linear Fletcher regression predictor. This is the generated sample. This is the theoretical loss function, the empirical loss function. These are the results in terms of the predictor and the original value of the response. Here we have the result for the local Fletcher curve prediction. This is the loss function in the case and the minimizer in the case of the Nadal-Wasson type Fletcher regression predictor. This is for the local linear Fletcher predictor, the empirical version for evaluating our local linear Fletcher regression predictor. The simulation, in the case of simulation study 2, we have the sample, the Fletcher curve mean, global Fletcher curve mean to apply logarithmic map to go to the tangent space for generating the response. And also we have here not only the curve response values, also our approximation by Fletcher Nadal-Wasson type local regression predictor. In red, we have the predictor, and in black, we have the original curve value of the response at different times. And also, we have, in the case of simulation study 3, the evaluation for the local linear Fletcher regression predictor from the simulated bivariate data curve sample in the sphere, the global Fletcher curve for evaluating the exponential map and logarithmic map, in this case logarithmic map of the regression to generate in the tangent space the response. This is the response value generated. The exponential map applied to this response value lead to this kind of curve in the sphere. And then we have the black curve for the response values, original observed response value, and the red the curve, the Fletcher local linear predictor value, and different times, and the summary of the angular functional errors. And finally, the real data application, which is our motivation, which is the prediction of the orientation of the magnetic field from the measurements of the NASA MASAT spacecraft. This kind of the spacecraft we know is go to every allows us to evaluate the performance of our predictor from 5-fold cross validation. With a good performance in terms of the 5-fold cross validation error, not only in the sense of the Nadal-Wasson time, also in the local linears. Some bad Y are also studied in different samples in different months for November 1979, and their references. I'm sorry because I have no time. So thank you a lot for your participation and for being here with us in this nice session organized by this International Day of Women in Data Science. Thank you, Eva.
Okay, thank you very much.